In calculus, tracking a sequence of numbers is usually a matter of observing where it lands. But in analysis, proving a sequence reaches a destination requires a more rigid framework. This leads to the Cauchy sequence, where points settle into a tight pattern without ever actually arriving at a landing spot. To understand how a sequence arrives, we first define our environment, the metric space. This is a set of points equipped with a universal distance function, denoted as d of xy, which provides a consistent way to measure the gap between any two items in that space. Inside this space, we define convergence as a sequence of points marching toward a target, x. We draw a circular boundary around that target with a radius called epsilon. If the sequence is truly convergent, that boundary eventually traps all following points, no matter how small we make the radius. This behavior is captured by the formal definition, the limit, as n goes to infinity, of the distance between the sequence and its target is 0. This definition forces two specific properties described in Lemma 1.42. First, the sequence must be bounded, because it is eventually trapped inside a finite epsilon bubble. Second, the target must be unique. If a sequence tried to converge to two different points at once, the distance between them would have to be 0, making them, by definition, the same point. Convergence, then, is entirely dependent on the existence of that specific anchored destination point. But what if we need to know if a sequence is settling down before we've even identified its final destination? We can shift our focus from the target to the points themselves. In a Cauchy sequence, we ignore the landing spot and simply measure how the points cluster. As the sequence progresses, the points clump closer and closer together, like a flock of birds maintaining a tight formation in midair. Formally, a sequence is Cauchy if, past a certain threshold n, the distance between any two terms, xm and xn, is less than our tiny value, epsilon. It is easy to prove that every convergent sequence is Cauchy. If two points are both approaching a single target x, the triangle inequality dictates that the distance between them must also shrink. If they are close to the target, they are necessarily close to each other. This leads to a common misconception, the idea that if points are clustering together, they must be converging to something. But in mathematical analysis, clustering alone does not guarantee that a valid destination actually exists in the space. Consider a metric space defined by the half-open interval from 0 to 1. In this specific universe, the number 1 is included, but 0 is strictly excluded. If we plot the sequence 1 over n here, the points march steadily toward the left. This is a Cauchy sequence. The points are clumping, but it cannot converge. The only possible limit, 0, has been deleted from this universe. The sequence is approaching a hole in the space where a point should be. To solve this, we look for a property called completeness. A metric space is complete if every Cauchy sequence is guaranteed to converge to a point that is also part of that space. We fill the gaps. Theorem 1.4-7 applies this to subspaces. For a subspace to be complete, it must be closed. If the boundary is open, a sequence can approach the very edge of the set and attempt to converge to a point that technically exists outside the subspace's domain. Theorem 1.4-8 further proves that when we have this stability, we can map convergent sequences through continuous functions, and the limit will travel predictably into the new space. Completeness is an essential structural property. It ensures that our mathematical environment is solid enough to support the limits our sequences are trying to reach. Mastery of analysis starts with these three pillars. Convergence is hitting a target. Cauchy behavior is the points clustering together. And completeness is the space's guarantee that the destination exists. As you move into advanced functional analysis and Banach spaces, these points expand. They become entire undulating function curves or operators, yet they still follow these same rules of clustering and convergence. This structure is what allows us to solve differential and integral equations. We can create sequences of approximations, and as long as we can prove they are Cauchy, completeness ensures they are narrowing in on a valid real-world solution. To continue deconstructing the principles of functional analysis, subscribe to the channel. Let me know in the comments which theorem or textbook chapter we should look at next.